Assalamualaikum and good day. I'm Puan Muslawati Muhajir, Science Officer in Hospital Pakar Kanak-Kanak. For this session, I will explain to you the topic entitled Quality Control and Quality Assurance. Okay, first of all, let us check what is the purpose of diagnostic of testing. First, it is for screening. It is to detect the early risk of a disease. Second, for diagnostic, it is to verify the diagnostic clinical, meaning that if the doctor suspect that the patient have a specific disease, in order to confirm his or her guess, they will do the diagnostic test. Third, to monitor the progress of a disease or treatment. Second and fourth, prognosis to predict the disease condition in the future. Okay, so let us check how the most of the diagnostic tests happen. If the doctor suspect that the patient have certain disease, the doctor will take small part from the patient's body, right? Usually, doctor will take blood, urine, which we call as specimen or sample. Then, lab will run diagnostic testing as requested by the doctor. Specimens will be added to certain chemicals or reagent that react with interest compound in the specimen we call as analyte. And the reaction between chemical or reagent with analyte will happen. Type of chemical reaction are such as changes in color, sedimentation, increase or decrease particular compound, and it will produce the chemical reaction product. The chemical reaction product then will be measured and represent the measured analyte. So, how to measure the chemical reaction product? Well, this is the table that lists some of the test reaction that will produce the chemical reaction product and the suitable method to measure it. So, for example, if the test reaction is chemical reaction, the measuring method is by using the spectrophotometry, nephelometry, tubidimetry, and many other. So, the measuring instrument will give reading that is not significant to the body's condition. The data is in example, optical density, electric voltage, thickness, and etc. This data need to be changed to more significant, such as weight of analyte, maybe in gram, yeah? Concentration, millimole per liter, enzyme activity, unit per mil, percentage, and any other. Therefore, calibrator is needed to determine the quantity of analyte. Okay, let us look at this example. We have the specimen and we want to measure the glucose. So we add to the reagent or chemical and it will produce the reaction product. Then we measure this reaction product using this spectrophotometry and it gives the reading of optical density equal to 3. So if the optical density equal to 3, can you guess the glucose concentration? Remember, the machine produce optical or electrical signal only. So let's say you have some materials with definitive value. We call this as calibrator, which is we have absolute glucose material with the concentration of 5 millimole per liter and deionized water. Of course, deionized water doesn't have any glucose, right? So the concentration is 0 millimole per liter. And using this material, we measure using the spectrophotometric and giving this reading, which is the absolute glucose give the OD reading is 5, and the ionized water, the OD reading is 0. So what happened next? We can generate the calibration graph. The y-axis is for the signal of the instrument, the OD, and x-axis is the concentration. So we go back to this previous specimen. Giving the specimen OD equal to 3. What is the concentration? Okay, look here. The signal of the specimen is 3. Then by using this graph, the concentration is 3 millimole per liter. I hope that you can get this, okay? So what is calibration? It is important process that links the analytical signal with the concentration of analyte. We use a calibrator or standard material, either single or series of solutions at known concentration. This material will be analyzed to get the calibration data. Calibration data will be used to develop calibration graph. This calibration graph will show the relationship between the concentration of the measured analyte and the magnitude of the optical or any signal given by the measuring device. By using the calibration graph, we can determine the sample with the known concentration, with unknown concentration by extrapolating the signal value from the measuring device on y-axis over to the analyte concentration, which is on x-axis. Okay, so as for summary, these are the components in quantitative testing. Of course, we need specimen which contain the analyte of interest. We need a chemical or reagent to capture the analyte that interest. We need analyzer or medical device to detect the chemical reaction. Of course, we need calibrator. And as additional, we need water because the chemical reaction happen in wet environment. And also, we need quality control. So how to determine that the components in the testing can produce correct result? Well, this point we need quality control. So quality control is to verify most of the component in test system so that it is in good condition. It is used to verify the calibration, chemical or reagent or solution. It is to verify the analyzer and water. However, QC is not suitable to verify the specimen or sample. This component need to be verified using the total quality management activity. As additional, QC also can be used to verify the operator and lab environment. If the operator is performing the test in appropriate way, the QC result may be wrong or violated. For environment, if the temperature is not suitable for the test, usually we need temperature room, it can also affect the QC result. So, why we need to perform QC? Before or during analyze the patient specimen? It is because we want to make sure that all the patient results are correct or accurate. So it is for patient safety. It is also for example, if the patient have end-stage renal failure and need to be on dialysis. However, the laboratory produced the normal renal profile instead of abnormal. This will lead the doctor of not performing the dialysis on the patient and could endanger the patient's life. So the function of quality here, first, to monitor the accuracy and precision of the complete analytical process, to detect immediate errors that occur due to test system failure, adverse environment condition and operator performance, and lastly, to monitor over time the accuracy and precision of test performance that may be influenced by changes in test system performance, example, reagent, calibrator or analyzer performance, and environmental conditions and variance in operator performance. So take note that QC does not monitor the pre-analytical and post-analytical process of the test. That area also could affect the accuracy of test result. Therefore, total quality management is used to monitor the error in pre-analytical and post-analytical area. So let us see what is the difference between QC and calibration this stage here. I don't want you to get confused between QC and calibration or calibrator. So QC, it is a substances similar to patient sample. The concentration consists of mean and SD based on a group of data from one lab or many laboratories. The function, first, checking the instrument's calibration and most of the analytical component, and second, to detect analytical errors and problem stability. So for calibrator, it is a substances with specific concentration which is traceable to test reference method. The function is to setting the analyzer to the test requirement, produce calibration curve that can be compared and estimate the concentration in sample. For QC, it is to measure the accuracy and precision of the test, prevent incorrect result, and help in troubleshooting. And also, QC should be performed after analyzing calibration and before or during analyzing patient sample, while calibration should be performed before analyzing the QC and patient samples. So, let's go to the QC material, QC type. It consists of two types. First, internal quality control. It is a set of procedures undertaken by laboratory staff for the continuous monitoring of operations and the results of measurements in order to decide whether the results are reliable enough to be released. This is to ensure the consistency of the results day to day. Second is external quality assurance. The other name is external quality assessment or proficiency testing scheme. It is system designed to objectively assess the quality of results obtained by laboratories by means of an external agency. So let us go to the internal quality control first. We look to the production of the QC, which is in the list. First, the dependent control. It means that the QC material is produced by the same company that supply the reagent and analyzer. For in-house control, meaning that the laboratory itself produce its own QC material. While lastly, independent control means that the QC material is produced by the different company that supply the reagent and analyzer. It is a different company from the reagent and analyzer company. This is also called as third-party control. So, under Laboratory Diagnostic Accreditation, MS-ISO 15189, this kind of QC material is necessary where possible. So now let me explain the property of the QC material. First, it should be same matrix as patient specimen or sample such as blood, plasma or urine. It is in lyophilized or liquid form. It contains analyte, either single or multiple. It is in aliquoted form. It have a known concentration, which is consists of mean and range. It has one or multiple level of concentration. And last but not least, the stability and volume should enough for certain period of time. So I will explain more on the QC properties. First, same matrix as patient samples, such as blood, plasma, or urine, and etc. So the QC material should be similar to patient sample as possible. For example, if the patient sample is in urine form, then the QC should be in urine form. If the patient sample is in serum form, then the QC sample should be in serum form. So how to develop this? This can be accomplished using the pooling actual samples of human serum, pooling animal serum, or using artificial protein-based solution that has same physical characteristic as human serum. Second, lyophilized or liquid. QC material could be in lyophilized or in liquid form. Lyophilized means freeze dry form. So there is contra and strength and weakness of the lyophilized and liquid form. For lyophilized, the material stability is much longer. It can be up to 3 years, while the liquid form, the material stability is much shorter. It can be 2 years or less than it. For lyophilized, it needs proper preparation during the reconstitution process, while for liquid form, it is ready to use. So no any other preparation. And please note that the lyophilized IQC, there is volume issue during the QC preparation. During reconstitution, we need to use the tool that could deliver volume with high accuracy. If the volume being used is not correct, then it can affect the concentration of the material in it. In this case, the analyte of interest. Usually, we use volumetric glass pipette with A grade. So I want to note here, reconstitution. It is the process of restoring something dry to its original state by adding water or solution in it. And number 3, the QC properties. It contains single or analyte, multiple analyte. IQC material can usually must contain analyte of interest. The analyte could be 1, 2, or more analyte in the QC material. For this example, this is the QC material for HbA1c. It just only contain HbA1c analyte. So this called as single analyte QC. Whereas this kind of QC, it contain the analyte of T4, TSH, ferritin, LH, FSH, and cortisol analyte. So this is called as multiple analyte QC. So QC that have only one analyte described as contain single analyte, while QC that have two or more analyte described as contain multiple analyte. Some QC are made as single analyte due to the stability of the analyte. If the analyte of interest is mixed with another other analyte, there could be reaction that can deteriorate the analyte of interest. Therefore, it is made as single. So here it is. This slide explains what I have said before. So laboratory usually use multiple analyte QC due to easy of use. Yeah, for one QC that have many analytes or many tests, save time, energy, and cost, and less error during handling. Number 4, aliquoted form. So most IQC are bottled in aliquoted form. Aliquoted means material is stored in small volume from a larger quantity. So usually QC material is stored in 1 ml, 5 ml, 10 ml, or maximum 5 ml. 5 ml volume. So after the QC being opened, the material will be aliquoted also into smaller volume. The purpose is to maintain the integrity of the analyte concentration, because once the QC open and take out from the store medium, it is subject to evaporation and easily change in concentration. So by aliquoting, only a small portion is taken out and used, while the rest of the IQC material still be stored and the integrity is maintained. So this slide I want to show you the different storage of QC material and chemical item. So this is the chemical material. Usually we can store in bulk of 1 liter or 2.5 liter, and we can take from time to time the chemical from it. But for IQC material, usually we store in 5 ml, or maybe in this example only 200 microliter. And when we prepare the QC material, we also aliquoted it into smaller volume. Yeah. So each IQC bottle need to be aliquoted to smaller volume, enough for analyzing before use, so that one QC bottle can be used for this one QC bottle can be used for several times. The aliquoted IQC is analyzed to monitor the test performance daily. This used QC need to be discarded because the integrity of it already deteriorate after usage. Some of the used QC can be used several times, depend on the manufacturer recommendation. Number 5, have non-concentration, mean or range. The concentration value of analyte of interest is obtained after being analyzed several times, a minimum 20 times in one or more laboratory. So mean will become the target value of the QC material, and range will become the acceptable value, meaning that it will become the minimum and maximum value that can be accepted. So this is the example of the QC material which have the value of mean and range of it. And this QC material, it have the two level concentration, which is level 1 and level 2. Number 6, it has one or multiple level of concentration. Most IQC material have two level concentration, which is either normal or abnormal, or maybe low or high. And some IQC material have three level of concentration, such as normal, abnormal, or very abnormal, or maybe low, medium, and high. For example here, this is the two level of IQC. It has the normal level and abnormal level. And the example of analyte is such as renal profile, liver function test, fasting serum lipid, and etc. And this is the example of three level of IQC. It has the normal level, abnormal level, and very abnormal or very high level. An example of the analyte could be renal profile, T4, TSH, FSH, and LH. And we seldom get the IQC material with one level of concentration. And please take note that the concentration should cover medical significant level or clinically important range of analyte concentration. Number 7, stability and volume should enough for certain period of time, because QC we need to use every day, and it is for daily monitoring of the test system. Therefore, the stability and volume should cover for at least 1 month. Maybe for hematology, it can only cover for 1 month, 6 months, 1 year, 2 years, or if we are lucky enough, maybe up to 3 years. And it is all depend on the analyte stability. Because the purpose, every batch of IQC have its own mean and range value. It is used for precision and accuracy monitoring for the test of the test in long-term run. So if we change the accuracy batch or lot, the mean and range value will change. Thus, it is difficult to monitor in long-term run. Okay, so the summary about QC, I have explained to you the purpose, QC type, and properties of QC. Now, I want to go on about how to produce the QC, develop the QC value, perform the QC, and interpret the QC. Okay, how do manufacturer develop the QC, or even you? Okay, first of all, we need to pull the sample until sufficient volume of usage, such as 6 months or 1 or 3 years. We need to pull the sample. And then this is the example of pooled human serum of 3 liters and 1 liter. And please take note that we need to consider the analyte of interest. Example, the QC material for renal profile and liver function test should contain the analyte of sodium, potassium, urea, creatinine, ALP, ALT, total protein, albumin, and bilirubin. And also it need to consider the level of IQC. Example, 2 level of IQC renal profile should have 2 pool of serum that contain normal, first normal concentration, and the second abnormal concentration. So some additives such as bovine will be added to the IQC to achieve that target level. Second, we need to run the sample of QC every day for at least 20 days, preferably 1 month or more. we need to analyze the put sample every day. Analyze the analyte of interest. Example, the IQC for RP, we need to analyze the analyte of sodium, potassium, urea, and creatinine. Then the control should be assayed over an extended period to ensure that it is subjected to changes in laboratory environment that may occur with different operator or at different time of day. And don't forget to record the data that obtained. So, usually when we calculate the data, after we get the data, we need to calculate the data. Usually we calculate the mean and SD of the QC data. So, theoretically, repeating same sample will produce same results. However, it is not happen and there will always be variation in results produced by the same sample. With a correctly operating system, repeat testing of the same control sample should produce a Gaussian distribution. Most of the data will be concentrated at one point and a small portion will spread far from that point. That is, approximately 68% of values should fall between plus minus standard deviation range and be evenly distributed on either side of the mean. 95% of values should lie between plus minus 2 standard deviation and 99% should be between plus minus 3 standard deviation. The remaining of 0.3% of the data theoretically spread out infinity. So how to calculate the mean and ST? So this is the formula of calculating the mean and the standard deviation of the control. In QC, mean become the true or the target value of that control. And SD, standard deviation, become the limit for acceptable of the control. Usually, we will use plus minus 2 standard deviation. So how to perform QC after we get the result? Meaning that after we develop the QC, now we can use that QC that we produce. Or if we buy the QC that have the mean and the data value of it, then we can use that QC, okay? So, we need to analyze the QC. When can we analyze the QC? Of course, before or during analyzing the sample, or beginning of each shift, or after an instrument is serviced, when the reagent lots are changed, after calibration, or when patient results seems inappropriate. QC results must be within acceptable limit before releasing the patient's result. So that's how we use the QC. And not to forget the frequency of analyzing the QC, according to CLIA, which is you can Google the meaning of it. It should cover 8-hour to 24-hour interval. Other method total number of specimen, which is if the specimen is less than 50 specimen per day, then we should run 1 QC level per day. If the number of specimen 50 to 100 specimen per day, then we should analyze 2 QC levels per day. If we got more than 100 specimens per day, then we need to analyze 2 QC levels 2 times per day. And after we get the QC data, QC result, how to interpret the QC results or QC data. So we used this method. First, quick checking. We just compare the QC result with the mean and SD limit, the range, and we just make sure that the value of the QC is within the acceptable limit, which is plus minus 2 SD. Second, we can use the Lever-Jennings chart. If it follow the Lever-Jennings chart target, then it is the performance of QC or test is okay. And third, we can use the Westgard multi-rule. So for Lever-Jennings chart, it is a graph that the QC data is plotted on to give a visual indication whether a laboratory test is working well or not. X-axis, meaning that it present the frequency of time running the QC, while y-axis represent the standard deviation. Y-axis, yeah. So the y-axis consists of mean and standard deviation of 1 SD, 2 SD, and 3 SD. Yeah. So you see here, this is the 1 SD, 2 SD, and 3 SD. This is the positive side, and this is the minus 1 SD, minus 2 SD, and minus 3 SD. Minus 3 SD, okay? And also it has two sections. This is the positive SD section, and this is the negative or minus SD section. The positive SD section is where the QC value is more than the mean, while the negative section is where the QC value is less than the mean. Y-axis show the deviation of daily QC from the mean of target value. If the QC data fall into around plus minus 2 SD, then the QC is accepted and the patient result can be released. If the QC data fall outside of the plus minus 2 SD, yeah, this is more than plus 2 SD, and this is less than minus 2 SD, then the QC need to monitor and take action, and the patient result may not be released. So the purpose of a Lever-Jennings chart, first it is to ensure that the data is within the acceptable range. As I mentioned before, that is plus minus 2 SD. And second, to detect small but significant error. First of all, let us see how do we can plot the daily QC data on Lever-Jennings chart. Okay, this is the example here. Let's say for this QC, the mean is 250 and standard deviation is 8. So from here we can put the mean here is 250, and we can put this is the 1 SD, 2 SD, and 3 SD, while this is minus 1 SD, minus 2 SD, and minus 3 SD. Okay, now let's look at the QC on day 6. Day 6, okay. The result of QC day 6 is equal to 258. So how to plot? Yeah, we can calculate the standard deviation index for QC on day 6. The data 258, we minus with the mean and divide with the SD. So we get the SDI index 1. So we plot 1 SD here. Okay, another example. QC data day 11. The result is 240. So how to calculate? 240 minus with the mean of 250 and divide with the standard deviation 8. So we get the SDI value of minus 1.25. 1.25. So here we plot the QC data for day 11. Okay, I hope that you can understand. So question, what is the SD for QC on day 15? I hope that you can answer that. It is very easy, okay? So, what is the target LJ that I have mentioned before? The target LJ is the QC data is near to the mean and the distribution is quite symmetry, which is the number of QC on the positive side is same with the QC number on the negative side of the section. Okay. However, some of the algebra chart will show this kind of pattern. Yeah, this kind of pattern, which is show the systematic error. It show in the pattern of trend, bias, or shift, or random error. So this is the pattern of random error. This is the pattern of trend. Yeah, this is trend, and also this is trend, and this is bias. Yeah, bias pattern, and this is the shift pattern. So, for systematic error, the change in control value are constant with predictable magnitude. If we see the trend error, it shows gradual increase or gradual decrease magnitude of the QC on the same side of the section, either positive side or negative side, and may eventually out from the limit. So for bias, consistently on the same side of the section, not symmetry, it may near to the plus minus 1 SD or more. And for shift, it is a sudden change in control mean. Sudden change in control data. For random error, it is change in control value that are not consistent and the magnitude is unpredictable. Okay, so another way to interpret the QC data, we use the Westgard rule. It is the rules that are used in conjunction with each other to provide a high level of error detection while reducing the incidence of false rejection. It uses different combinations of rules depending on the number of controls being used and the total allowable error. The purpose is to detect high error detection and low false rejection. And this is the typical rule combination. If we use two level of QC, these are the rule that we use: 13S, 12S, 22S, R4S, 41S, and 10X. Usually we use in chemistry test. And for controls that run in 3 levels, example for immunoassay test or hematology, these are the multi-rule that we use, multi-Westgard rule that we use: 13S, 2 of 3 2S, R4S, 3 1S, and 12X. So let's go deeper into one by one rule. For 13S, it meaning that one QC data has violated the 3SD. So it indicates shift or systematic error or increase in randomness. The action we need to reject run, and we need to troubleshoot whether it is random error or large systematic error. How about 1 to S? It means that one QC data has violated plus minus 2 SD, yeah, as shown in this example or this example. So this is the warning rule. What is the action? We need to repeat run. If the second run is okay, so then we doesn't need to reject the sample run. We can just release the patient's result. However, if it is always occurred, then we need to monitor for possible cause. Usually, maybe because of the quality stability after thawing process. Okay, 2 to S or 2 of 3 to S. For 2 to S, meaning that 2 QC data has violated plus minus 2 SD, is shown in this example or this example. It indicates systematic error, potentially affecting a specific portion of method curve. So the action may require run rejection and need to do the troubleshooting. For 2 of 3 to S, meaning that for the 3 levels of QC, 2 of the levels have violated. So R4S mean that 2 data, subsequent data, have distance of 4 SD, as shown in this example. One QC data in minus 2 SD and another QC data, subsequent QC data on the positive 2 SD. So the distance between it is 4 SD. Same goes with this. This is in plus 2 SD, but another subsequent QC is minus 2 SD. It is already violated. So the distance between it is 4 SD. So this indicates random error, potentially affecting a specific portion of method curve. The action may require run rejection and need to troubleshoot. For 41S or 31S, 41S meaning that 4 QC data has violated between 1 SD to 2 SD, and it is consistent in one side. And same goes with this example. And please note that for 3 levels of QC, 3 levels of control, it uses the 3-1S rule. It can mean in one run, all the QCs are on the same side and between 1 to 2 SD, and one level of QC show on the same side and between 1 to 2 SD area. Shown this example. Okay, now how about the 10S or 12X rule? So meaning that, please note that for 3 levels of QC, it use 12X rule, while the 2 levels of QC, it use 10 levels rule. It can mean in all run, all the QCs are on the same side and not exceeding, and most of it not exceeding the plus minus 2 SD. It is within plus minus 2 SD, however, only on the one side. So for 12 QC data, also it is on the same side and not exceeding plus minus 1 SD. regardless of any QC levels. So it is indicate systematic error, may signal a change in analytical characteristic of system, example control load or care load, and usually is not a clinically significant bias. So the action may not require random rejection, may not require immediate action, may not be indicator to perform, but it is maybe indicator to perform maintenance or calibration. Therefore, we need to check all components of the test. So, how to troubleshoot? Well, we can use type of error as guidance. Okay, for random error, we can see it is changes in standard deviation. The random is outlier and there is random direction. So it represents imprecision or maybe inaccuracy. The magnitude is not predictable. In level Jennings, it shows as random distribution. In Westcott material, it is showed as 1,3S or R4S. For systematic error, the change in mean of control value remain constant or predictable magnitude. It represents inaccuracy or bias of method. In level Jennings change, it present the level Jennings trend, which is indicate gradually loss of reliability in test system. In LJ shift, it shows abrupt change in mean, indicate change in test system. Example, maybe there is any lot change of reagent or QC or calibrator. And in Westcott material, these are the rules that shown for systematic error. So for random error, what is the possible cause? It can be caused by bubble in reagent line or instrument line, inadequate mixed reagent, unstable temperature, and many other. I hope that you can read it by you yourself. Okay. And for systematic error, these are major possible error, such as change in reagent, calibrator or control, wrong care or control values, improper prepared reagent, care or control, and many more. And this is maybe the possible error if we see shift pattern of the LJ chart. And this is the possible error if we see the trend pattern of the LJ chart. And please take note that this is not the definite cause. Other cause than this may give error to the test system. So you need to understand the test system, which is you need to refer to the test principle nature. Maybe you need to read the textbook, or you need to study the system involved. Yeah, maybe you can read the insert of the test, the manual of the instrument, or if there is standard operating procedure, then you need to study the SOP. And for real life, you need to hands-on the instrument or you need to hands-on the test itself. So with this, I end my presentation. So thank you and good luck.